So we're sitting here at the University of Bristol, and this is take 2. Because my flu brain forgot to remind me to turn on the record button. Anyway, we're having a really interesting conversation with Tom Deakin, who is part of the performance portability team here at the University of Bristol in Computer Science School. And now, Tom, you gave a really interesting talk at supercomputing on our booth about the performance portability aspects of a lot of the exploration that you'd done, including on Graviton3, but also on several other processors. And this is a really interesting area to us, and because there's a lot of in the cloud there's a lot of different CPU architecture options, and we want to be able to make it possible for folks to explore all of those and find the sweet spot for their code. You're looking at this from the other angle and looking at how well do the software stacks optimized for those different areas. And I think it's definitely of mutual interest. So can you take us through some of the discussion that you led on our booth at AWS, and then give us some of these insights of what you've been able to determine so far?
Yeah, so it was great to speak at the booth at Supercomputing. It's always a fun conference, and it was a busy conference. It was great to catch up with everybody, and yeah, so kind of just as a quick rundown of some of the bits of the talk. So we were interested in looking at the Graviton processors in AWS. They're ARM-based, and they seem to offer really compelling performance numbers, right? If they're ARM-based, they seem to get us really great performance on paper. What we wanted to explore actually for our benchmarks and applications is that the case? And we've been interested in ARM for HPC for a long time. And in Bristol, we have the Isambard supercomputer as one of the first production ARM supercomputers, full of ThunderX2 with a bit of ARM. The A64FX from Fujitsu, the Fugaku is the second biggest machine in the world. Yeah, I mean, the work that we've been doing in ARM is showing that the move from x86 to ARM is generally easy, right? The software ecosystem is great now. All the tools work, all the compilers work, and generally it's just a case of recompiling and away you go. And you guys you're not responsible for a small amount of that. You've contributed quite significantly to making sure not only that the tooling works, but the tools work. And the things do just build. So it's actually, when we had the hackathon a couple of summers ago, it was quite eye-opening how, actually in the end, how not hard it was to get an awful lot of things working and compiling. Yeah, and that was one of the goals of Isambard when it first, the very first Isambard supercomputer came up, was to make sure that that was the case and was going to be the case for the future. So yeah, Graviton3 and Graviton2 is both really interesting ARM processors, but only available in the cloud. So it kind of opened up these questions of, well, what other opportunities are there in the cloud? And with the kind of performance portability slant on it, we're interested in trying to get good performance across all processors we care about. And the cloud is really exciting and interesting because I can get whatever architecture I like at the click of a button almost immediately, right? And so I'm interested in exploring ARM for HPC and the ARM processors, but then start to build that out into understanding performance of applications across all the different architectures and what that means in a cloud environment, right? How can I run those experiments, and how can I explore the latest thing that comes that I can get hold of in the cloud? Because
even just inside the x86 space, there's multiple CPU architectures there, and we've got a lot of those. And there's multiple AMD architectures, multiple Intel ones. There's interesting attributes of all of those chips that some codes can exploit well and truly to their benefit. Yeah. Not just this sort of x86 ARM discussion. It pivots around a bunch of different angles.
Yeah, and with GPUs too as well, right? Maybe you use GPUs and they should form part of the discussion too.
And an increasingly diverse set of accelerators, but let's not go down into
Yeah, exactly.
Because you're right, there's a lot of them.
So yeah, the first kind of thing we're interested in is, well, just some basic feeds and speeds, right? What sort of base performance can we get out of some benchmarks that give us a tangible way of reasoning about real science codes that we care about? So one of those benchmarks is called Babel Stream. It's based on a very kind of traditional benchmark called Stream, but it's modernized it, so the compiler doesn't know how big the problem is at runtime, and it essentially is written in a way that we would write codes today. we also have implemented it in 12 or 15 different parallel programming models, which puts the other different space on it too, right? Ultimately, you want to write your code in a way that works well for your algorithm and for your application. So exploring a range of benchmarks across a range of different implementations of that benchmark on a range of different architectures, it becomes a very complicated space that we're trying to explore.
And how easy is it for you to, I mean, I want to understand a bit more about BabelStream. It sounds like with BabelStream, you've built it to not just challenge the hardware, which is that's the scenario that I'm used to seeing is a benchmark is challenging my hardware, how does it perform? But also you're challenging the software stack and more to the point, the compiling, the compilers themselves.
BabelStream is often a test of build systems because we want to have an application that's quite unified, but with specialized implementations essentially in different program models of the same piece of fraction of that code, right? So we need a build system that is going to get all that running. And so far we've kind of cobbled it together with bash scripts and things, but I'm exploring in a project at the moment to build on a lot of the fantastic quality tools with SPAC and with Reframe, because SPAC should solve all our problems for this, right? It helps us work out how we can get all the dependencies we need, how we can then build the compiler perhaps against those dependencies, and then build our application against all of those things that we need. So if I want to build BabelStream with OpenMP with GCC, I should just be able to say that and do it automatically. And ultimately then do an experiment that tests all possible combinations on all possible architectures, and then run them and get all the performance results too.
It's not quite as easy as I want to explore these 3 CPUs with these 5 codes, go make it happen. It's not quite that easy yet, is it?
Yeah, not quite yet, but I think it should be, right? It should be that easy, and I think the tooling is the way forward is kind of clear, right? SPAC and Reframe together should be able to enable that experiment. So I think as it kind of grows and more applications are built within that framework, and then more systems are understood by Reframe. Reframe, you have to teach it how to run a code on a system, and then you can run any code on that system, right? So once I think the coverage of all of those things is done and hopefully upstreamed, then it should make it easy for everybody, right? You just need to bring your application, build it with SPAC, and then everything else should come along for the ride.
That makes sense.
So yeah, I mean, we ran BabelStream on AWS. We looked at Graviton 2 and 3 and compared it to the CPUs in Isambard, the Thunder X2s. And yeah, it was great. We were able to see that we were getting close to 80 or 90% of the theoretical peak performance with OpenMP and GCC, one particular implementation, and could just really see if I then run a proper application, what performance might I expect if I ran it on Thunder X2 or Graviton 2 or Graviton 3, knowing that it was memory bandwidth bound. So running a quick and simple benchmark enables me to do that. So yeah, we had a fantastic intern over the summer. This was a graph that Rob Jones produced for us. And yeah, comparing for the different kernels in BabelStream, the performance that we were able to get. And higher is better. We were getting close to that theoretical peak performance with Graviton 3, which was kind of cool to see. You can definitely see those improvements from Graviton 2 to Graviton 3. There's a kind of a step jump in the theoretical, but also in what was attainable, right? The Graviton 2 was great. You could get close to that peak performance too. And because of those engineering enhancements, you can also get that in Graviton 3 as well. But it's not all about memory bandwidth necessarily. Some of the kind of stranger HPC codes we have to worry about can have a performance impact on the other bits of the memory hierarchy, things like caches. So yeah, Rob produced some other graphs that measure the bandwidth and latency from each of the levels of cache. There's a lot more digging in here. Understanding a cache hierarchy is quite complicated because they're designed to not be visible. The processor is essentially helping you get better performance out of memory access without you thinking about it in your code. But if codes now start fitting in small bits of cache, then you start having to kind of you observe the side effects of the cache rather than you're not directly programming for the cache. There's no way of controlling, put this here and put this bit of data there, right?
If only.
If only, that would be amazing. But so yeah, trying to understand this is complicated, and different architectures have different implementations of how they do this. But just kind of understanding the different performance characteristics is super interesting. And again, the cache performance and the bandwidth of the processors it's on the graph, but it's kind of super interesting. And this is the latency too. The latency is interesting for if you have something that's kind of really horrible that doesn't have a regular access pattern, something that jumps out around in memory. So if you've got an unstructured mesh, you have to go and jump around memory all over the place. And yeah, it was kind of interesting. Something we want to investigate a little bit further is normally when you fall out of L2 into L3, you could see on Graviton 2 it was quite a big penalty, right, for doing that. But that penalty is much reduced on Graviton 3. So there's a lot more understanding, I think, that we want to do for really understanding at a microarchitectural level what optimizations have gone into that architecture to help for these different applications that need to think about that. So as part of this kind of performance portability, you need to write your application down, right? You have this scientific problem and you need to write a program that solves that. And so you choose a programming language to write it in, C or Fortran, but you also have to express the parallelism in there. You have to write a parallel program. So you choose a parallel programming model to let you do that. So part of BabelStream, as we said, is to explore the different parallel programming models, each of which are supported by multiple compilers. So yeah, here we've got two applications, BabelStream and MiniBude. MiniBude's a very compute-bound code. BabelStream's a memory bandwidth-bound code. And we're trying it on Graviton 3 in a bunch of different programming models across a bunch of different compilers. And these graphs really, essentially, if you read them left to right, you want to be as close to one for as long as possible. As you add more and more compilers into the mix, you're essentially adding in the least efficient compiler for your code. But what was kind of cool is you could find a compiler and a programming model that would run well. And for any implementation in the programming model, you could write it in, you could find a compiler that would get good performance too.
But so, okay, so the challenge, of course, is to try and stay as flat on this graph as possible.
Yeah.
How did we do? And more to the point, I guess, how did the different compilers do? Because it's
so this is great. Yeah, so for a memory bandwidth bound application like BabelStream, essentially it didn't really matter what compiler you picked. They all got close to the peak performance in whatever model that you saw.
And that's interesting because BabelStream was designed to make it hard for the compilers.
Yeah, exactly.
So it's cool. Okay,
that's really cool.
That's a good result.
But BabelStream just means the compiler has done a good job in moving memory, right? It's scheduled the memory movement and not done anything strange in how it's moving memory around. But that's relatively slow to do. Moving memory is slow. You've got hundreds of clock cycles where you could be doing arithmetic, but you're just waiting. This is why we also test the compute-bound case where the compiler has to do a really good job of that arithmetic. And if that's the bit that it's bound by, then it has to do a much better job, right? You're talking of, is it doing a good job on the cycle level rather than a good job on the hundreds of cycles of levels? So yeah, accessing memory is so slow that you can kind of hide all manner of horrible things behind it in the code that's generated by the compiler. So yeah, with a compute-bound code, we find other compilers. Really, it's how they improve over time in optimizing for a particular architecture. They have to, as the compiler grows in maturity and its knowledge of how to generate code for a given generation of a processor, we have found that it's able to provide better performance over time. But this is obviously just a single snapshot of a particular.
So some of those longer-lived compiler suites, and the NVIDIA HPC compiler has quite a long lineage, right? It's been around for a long time, so it's GCC.
Yeah.
That's where they pick up experience over time at different architectures and being really good.
Yeah.
Interesting.
Yeah. So parallel program models is one thing, but maybe we can not worry about those. Maybe we can just take advantage of the main languages that we write in. So in HPC, the common kind of candidates are things like Fortran and C++. But those languages have ways of expressing parallelism and concurrency directly in them. So maybe you don't need OpenMP anymore. Maybe you don't need OpenACC. Maybe you don't need any of these things. Maybe you can just write in C++ or write in Fortran and get your job done. So this is kind of new research, and it was nice to share it at Supercomputing, both on the booth and with some colleagues at NVIDIA in one of the workshops. So yeah, this is a little bit of an eye chart, but it's the same BabelStream benchmark, but now written just in Fortran. So I don't worry about OpenMP. I just say, here's a parallel loop. It's do concurrent. That's how you spell it in Fortran. And you give it to the compiler, and we tried it on Graviton 2 and 3. And yeah, we got just the performance that you'd expect with at least some of the compilers, particularly with the NVIDIA compilers. You could just say, do concurrent, and it would run, and it would get you close to the same performance you'd get with some other parallel program model. So it's early days maybe with the Fortran side. And the standard is improving to allow you to express more kind of complicated things like reduction operations. But yeah, I think it's an important step forward to maybe just how far can we get just writing regular Fortran or regular C++. So that's the Fortran story, and this is the C++ story. This was a chart that Tom Lin produced. And again, there's lots and lots of data points here, which I'm not going to go through. But this looks at Graviton 2 and 3, but also x86 with Intel and an AMD processor.
Right.
And it's kind of the more red, the better, right? It's close to 100% of peak performance. So it's, again, we're talking about main memory bandwidth. And yeah, this was interesting. This is just using ISO C++, comparing to the other models. And there's different ways of expressing a parallel loop in C++. So you've got database like standard transform, or index parallelism like standard for each. So kind of a subtle semantic difference, which I won't kind of go into, but it's, is my data, do I know where I am in my parallel space, right? Do I have an index? Can I think about who my neighbors are, or I'm not allowed to know who my neighbors are? Essentially on Graviton 2 and 3, you see this big red box on the chart, right? So that just means we get good performance no matter what we wrote it in, including things like standard C++.
Wow.
Which was really great. Trying with different compilers. So this is testing GCC Clang and NVIDIA, the NVHPC compiler too. And yeah, it was great. For the memory bandwidth bound Babel stream, it was basically didn't matter what we wrote it in, it was getting good performance everywhere.
And we start to see contours develop once we go below that, I guess, onto... So these are onto the Intel and AMD architectures. What's going on there? What do you think is going on?
Yeah, so these are essentially different characteristics, right? The way that we access a Graviton processor is we get access to a single socket, and you build a compute node, an EC2 instance out of a single socket of Graviton 2 or Graviton 3. And the next one is kind of a whole separate node away in HPC kind of language. But we tend to buy dual socket systems for Intel and x86
sure.
for AMD and Intel. And so for our Xeons and our Epics, they are dual socket machines. And so the memory behavior, the non-uniform memory access or NUMA behavior you get between those dual sockets, I mean, Babel stream is written so that it's aware of that, and you should be able to get good performance. But this is where it starts testing the compiler technology and the parallel runtime technology that it kind of comes along with that. And we're finding there's some strong NUMA behavior with some of the models, just as having a dual socket with this NUMA behavior is challenging. If you look at how those systems are developing, there is stronger behavior even within a socket, on some of those architectures. So making sure applications are aware of NUMA is the first step, but also making sure that that information is not lost, and the quality of the compiler and the implementation can also meet at that same boundary and make sure that the NUMA behavior it chooses to use is good. So yeah, that's kind of some feeds and speeds again, but thinking about the programming model aspect. And as part of one of the interns over the summer started looking at some bigger applications. So this is an application, science code, a mini app from the Asimov project. It's based on a Rolls-Royce CFD, a computational fluid dynamics code. We then started looking beyond just a single instance of Graviton. Can we use parallel cluster and build a cluster on AWS that enabled you to run a scientific code? And for here, we found that Graviton 3 was slightly faster than Graviton 2, some more digging into actually, well, what is the bound of this code, right? Maybe it's not completely bound by the data movement, right? So there's some work we have to do on the application. So that's it, really. Yeah, that was all the kind of the main stuff. In Bristol, we've been really excited about trying the clouds, and I think it's in a really interesting space. It's interesting to explore the brand new architectures as they come out. It's interesting that you as a cloud vendor are developing your own processors and your own silicon optimized for your customers, right? But that includes us as HPC users too.
Right.
So understanding those the performance that we can get out of those relative to everything else is kind of super interesting, and how easy is that migration as well. But also kind of the impact that having the choice of different architectures available to us, and what pressure that puts on us as application developers to be ready for that, so that we can try out all this stuff and be confident that we're getting good performance on whatever we try, and hopefully then improving our applications so that they can perform well everywhere, and hopefully working with the vendors too, right, to say, well, this specific instance of my application on this processor with your compiler needs some improvement, and help essentially make it great so that we can write our codes in whatever we like and run them on whatever we want and get great performance.
Well, as usual in HPC, it's a constant interplay between the application and the hardware. And of course, there's a bunch of stuff in between the application and the hardware. But for the first time, it feels like in my career, the first time we're entering a new age where we are breaking ground on new CPU, GPU, accelerator architectures, and we've got an ability to create automation to explore the problem space and gather the telemetry we need so that we can say we need to send the ambulances over there because that's where the performance, that's where there's a performance pocket that needs addressing. And hopefully being able to give customers visibility into that data so they can say, I want to drive around that pocket. I want to navigate my way to this CPU architecture over here because that's where my application is going to work best. Both of those things have got a lot of value to everybody. Anyway, so thanks for the interesting insights. Thanks for the talk that you did, of course, at our booth at SC. And thanks for all of the ongoing work to explore this space.
Great. Thanks very much.
If you learned something from this talk, then please consider giving us a like and subscribing to the channel so you can find out when more videos like this are available. And if there's an area you'd like to see us go deeper into, don't hesitate to reach out and let us know. See you next time.